Hey everyone, today we are going to do a special lecture, and this question comes from the comments section of the Nucleophilic Substitution and Elimination course. So the comment here says, "Thanks very much. Could you please make a video on rearrangement reaction mechanisms? Thanks." So I'm going to address this in our video today, and we are going to tackle rearrangement mechanisms in SN1 reactions. So just a reminder, if you ever have questions and you don't see them addressed in the videos that we currently have, by all means leave a comment, because I'm here to interact with you guys and I would love to teach you something that you have a question about. So leave those comments and interact with the channel and I will do my best to address them. So let's get started with rearrangement of SN1 reactions. Alright, so SN1 product rearrangement. What is a rearrangement when we get to these types of reactions? And this is not exclusive just to SN1. You can have rearrangement in many different types of reactions. But the key is that you're going to need a cation. Specifically, when we're dealing with organic chemistry, we're talking about a carbocation that needs to be present. Alright? So in an example with SN1, we have a structure, and that structure has a leaving group. The leaving group is going to be displaced, and we're going to have a nucleophile that will come in and take the place of the leaving group. So the idea here is that the nucleophile is now in place of the leaving group. However, in certain cases, what the predicted product would be is not what you initially think. So this example right here, that I obviously drew on purpose, is incorrect. So the correct answer would be to draw this structure, the methyl group down here, and then the nucleophile here. And so the question is, how did we get to this structure? What happened mechanistically that moved the nucleophile from, if the bromine left, we would expect a carbocation in this position, and then we would expect the nucleophile to come in and bond to that carbocation. So if that's the case, then what is going on that created this shift? So how and why does the shift occur? And we have to look at the carbocation and understand carbocation stability. All right, now we have separate videos on the channel regarding carbocation stability, hyperconjugation, the reasons behind that. But what you really want to understand here is that tertiary carbocations are more stable than secondary, which are more stable than primary, which are more stable than methyl. So methyl carbocations don't exist. It would be very difficult, if not impossible, to get primaries. Secondaries are plausible. Tertiaries are very stable. So most of the time, we're going to be sticking to this region where we have secondary and tertiary. And rearrangements happen when you're going to find a secondary position next to a tertiary position. And specifically, if you have the cation on a secondary position and it is next to a tertiary position. All right? Now there is another position called a quaternary position, and we will talk about that briefly in a few minutes when we start talking about the types of shifts that can occur for a rearrangement. All right? Now, let's take a look at this in more detail and what's going on. So the example that we had above, let's rewrite that. All right? And we're going to write it out in a little more detail. We have the methyl group here. There is an understood or implied hydrogen right there, and the bromine. All right? And let's give a specific nucleophile. In this case, we'll just say water for an SN1. It's a good neutral polar protic use. So the leaving group is going to leave, mechanistically speaking, and that will leave behind a carbocation. Now the carbocation that's left behind is going to be initially where that leaving group was. So it'll be right here on that secondary position, and then we've got the methyl group and we have the hydrogen. Now this is important. You have to realize that you've got a carbocation in a secondary position that is directly next to a tertiary position. And when it is, this is important, it has to be directly next to it. But when it is directly next to it, the carbocation has the ability to essentially upgrade itself to a more stable position. And it does this through what's called a shift. So it will shift one of the two groups in the adjacent carbon, and it will move it over in order to create a new carbocation in the tertiary position. Now, in general, we will migrate the smaller group due to steric constraints. So in this case, we have a hydrogen and a methyl group. Hydrogens are certainly smaller than methyls, and so we get what's called a hydride shift. And this hydrogen with the bond, the electrons have to come with it in order to create a new carbocation, are going to move to that position. Now when this happens, a new carbocation forms in the tertiary position. And the tertiary position is more stable. It offers more hyperconjugation. Okay, now keep in mind that hydrogen is now sitting over here. You don't necessarily have to write it out. It could be implied at that point. And you have a new carbocation in the tertiary position. This then is what the nucleophile, and we said we were going to use H2O, would end up attacking. And that is how you end up with the nucleophile in the tertiary position when you see it with the product. So this is an example of a rearranged reaction. Okay, now there would be an additional step in there where you would have to deprotonate the water. But the bottom line is you end up here, and you would have your OH group right here instead, because that's where the water attacked. All right? So the next thing we want to focus on here are that there are two types of shifts. So the first one we just discussed is a hydride shift. That is when you have an adjacent hydrogen that can move over, bringing its electrons. The term hydride refers to a hydrogen that has a pair of electrons associated with it. Okay, so a hydride shift comes from a neighboring hydrogen with the carbocation, and that's exactly what we just saw. It shifts over, and then we have a new tertiary carbocation. Now notice, this is a tertiary carbocation. Sometimes students will ask, well, what would happen if there were two hydrogens there? Well, in that case, if there were two hydrogens, we'd be talking about this is secondary, where the carbocation would reside, and this would also become secondary without the methyl group there. And there is not any sufficient rearrangement because there's no need for a carbocation migration. It's not going to get any more stability from another secondary position versus the secondary position it's already in a case like that. So we don't consider examples like that. All right. Now the next one is a methyl shift. And a methyl shift is very similar. Sometimes this is also known as an alkyl shift, okay, because it can occur, that's a K. So alkyl shifts can occur with things like ethyls and propyls and things of that nature, but methyl tends to be the most common. We usually see methyl shifts in most undergraduate classes. Now, in a case like this, you're going to have a pretty similar setup, but now you have two methyl groups or two alkyl groups instead of the hydrogens. And in a case like this, you still have a secondary and you have the potential for a tertiary position next to it. So instead of a hydrogen, you're going to shift over an alkyl group or a methyl group in this case. And under the same general premise, you will end up with a carbocation that's tertiary here. But now you have really altered the structure significantly more because at this point you have brought a methyl and shifted it over. So when I say altered the structure, you basically created a structural isomer because you've really played around and shifted the components there that you're working with. So keep in mind, isomers, they have the same molecular formula, right? But they can have different rearrangements, structurally speaking. So again, you could set it up with some other type of compound. Just to show you another example, let's say we have a six-membered ring, right? The six-membered ring has a leaving group here, but it also has two methyl groups up here. So we've got a methyl here and a methyl here, right? If the leaving group leaves, now this is also important because this is for SN1. We need the carbocation. So we're not talking about SN2s where there's no carbocation intermediate. Because the whole point of the rearrangement is it's stabilizing the carbocation, right? So here's secondary. You've got your two methyls. You're going to shift one of these methyls down, and you would end up with a rearranged intermediate that looks like this. All right, and then the plus would be associated with that carbon there on the corner of the ring. So this is how SN1 undergoes rearrangements. And then the nucleophile, whatever it may be, is going to come in and attack that new positioned carbocation. And what results is that we get a compound that is different than what we would have originally expected, right? So here you've got a methyl, and this doesn't even cover stereochemistry, which is another topic. You can get isomers, stereochemical isomers, when you're attacking sp2 hybridized centers, right? Because they're trigonal planar, they're flat, they can be attacked from both sides. But the point here is the rearrangement reaction, where you now, instead of what you may have originally predicted, which is if you didn't understand rearrangement, you just see the leaving group and you go, okay, so the nucleophile comes in, right? The leaving group leaves, it leaves a carbocation, the nucleophile comes in, and then the nucleophile would be here. And your professor marks that as incorrect, and that's because you would have had a shift that should have occurred in order to promote stability of that intermediate carbocation. So hopefully that addresses SN1 product rearrangement or rearrangement reactions, because again, this can extend beyond SN1 whenever you have a carbocation. So if you found this video helpful, go ahead and leave a like. As always, if you comment, we will try to interact with you. You can certainly make requests, and we always appreciate any feedback, constructive or otherwise. And remember to subscribe and hit the little bell, because that is how you are going to get up to the date, up to the moment notifications and stay up to date during the semester. So other than that, thank you so much for learning with us, and we will see you guys next time.